Now, the previous topic we have taken before is what we call variable loads without stress concentration. Now, we are going to take variable loads with stress concentrations. Now, this topic that we have now is a little bit complicated. So there are so many factors that we have to take into consideration. Just like what we have taken from or taken in variable loads without stress concentration. Because in there, we have taken what we call the endurance strength. In considering the endurance strength, we will be having different factors that will affect the ultimate strength or the design strength, the design stress that we are going to use, which is referred to as the endurance strength. So there are actually factors which we consider as the size factor, the surface factor, the endurance ratio factor, which considering the endurance ratio factor, we will still consider whether the system is subjected to an axial load or subjected to a torsional load, which is a load in terms of torsion will be considered as subjected to shear in torsion. So those factors will be taken into consideration in taking the endurance strength. But we must be careful in considering whether the system is subjected to axial load or subjected to shear in torsion. So those considerations in taking the endurance strength for variable loads without stress concentration will also be considered in taking the endurance strength for variable loads with stress concentration. First, we try to consider what is stress concentration. The stress concentration meaning there is what we call a stress ratio, which by definition, the stress ratio is any discontinuity or change of section, which will result in a concentration of stress or localized stress that is greater than nominal stress. Now, this stress ratios that we consider is example is scratches or holes, notches, bends, groove, or fillets. Now, these stress ratios can be seen, or there are sometimes stress ratios that are needed in a given element or in a given system. That is to correct or to check other effects, external effects on the system itself. So why don't we just try to remove these things so that we will not have stress ratios? But there is a necessity. There is a condition that we will need stress ratios to check whatever is needed on the design. Like, for example, to remove some vibrations. When a certain shaft is subjected to torsion, there will be some vibrations. So to check a vibration or to check vibration on the shaft, say what we call holes. That is sometimes a central hole, sometimes a groove, sometimes a fillet. That is to minimize vibration. Now, the in considering the use of the equations involved for variable loads with stress concentration, we will need what we call this theoretical stress concentration factor. This theoretical stress concentration factor is referred to as K with a subscript T, which this stress concentration can be taken from theoretical analysis or a photoelastic study, which design of machine elements by Virgil Moringfield have already taken some experimental or analytical values that will be used for considering KT, which is taken from figure AF5 inclusive to figure AF14. That is for design of machine elements by Virgil Moringfield, together with table 8012 and 8013. So we will consider that the maximum stress is equal to Kp multiplied by the nominal stress. This is the equation or the formula for considering maximum stress. The value of the theoretical stress concentration factor Kp can be taken from the use of figure AF5 to figure AF14, table 8012 and table 8013, where of course S max is maximum theoretical stress due to some discontinuity. Then S sub O is nominal computed stress, which of course nominal computed stress is the stress that were taken before for simple stresses. That is, nominal stress in here is equal to F over A, or MC over I, or TC over J. That is for axial loading and torsional stresses. Now there is still, or there is also a factor that will be used for considering the endurance strength for the variable loads with stress concentration, which is referred to as Q. That is the Notch sensitivity factor of different materials, which is taken equal to Q is equal to KF1 all over KT minus 1. That is Q is equal to Kf minus 1 all over Kt minus 1. Or we can consider Kf is equal to 1 plus Q times the quantity Kt minus 1. Well, of course, we will be having Q as the Notch sensitivity factor. Kf is the fatigue strength reduction factor. Fatigue strength reduction factor, that is for Kf. And Kt, that is the theoretical stress concentration factor we have taken in there. So therefore, we can also take Q equal to 1 all over 1 plus A all over the small letter r. Now, this small letter r is what we call the radius of curvature. The radius of curvature of any of the stress racers. So, that can be taken from figure AF7, page 584 of the design of machine element by Virgil Moringfield. And this A is the typical values of a for normal stress with corresponding SU or ultimate strength, which is taken, that is for steel. The recommended values of A can be taken from an SU at 93 KSI with a corresponding value of A at 0.005. With SU at 180 KSI, that will be the A will be equal to 0.0005. Now, the value, if the ultimate strength is not 93 or is not 180, that is within the range of 93 to 180, say 120. So that is within the range of 93 to 180. So what you are going to consider in there, to find for the value of A for an ultimate strength of 120 KSI, you just try to interpolate it with these preferred values. So these are suggested values by Pierre Morintes for considering the value of A. If it is beyond, out or less than 93 KSI or more than 180 KSI, what you are going to do, of course, is to extrapolate for the value of A, which A, of course, will be the one that will be used for considering the notch sensitivity factor here. Because the notch sensitivity factor will be used for considering the fatigue strength reduction factor. Now, the significance of considering the fatigue strength reduction factor is by using the variable stress equation with fatigue strength reduction factor, that is Kf. Of course, for normal stress, we will be considering the Soderberg line criteria. The same thing with shear in torsion. We will still be considering the that is the Soderberg line criteria. We will not be using anymore the Goodman line criteria or the Goodman line equation. It is because that will be taken for considering the Soderberg line criteria for shear in torsion. Because Goodman line equation is only used for brittle material, which will not be considered. Brittle material will not be considered in considering a variable loads with stress concentrations. So these are the equations or the formula that we are going to apply. Now, take note of considering the endurance strength. The endurance strength in here will still be the same. Endurance strength that we have taken for variable loads without the stress concentrations. The difference is we will be having the fatigue, the strength reduction factor here. That is K with a subscript F. The same thing with shear in torsion. Only we will be indicating that this is shear in torsion with a subscript S. Now, going back to variable loads without stress concentrations, for considering the endurance strength, we have taken previously that the fatigue limit or the endurance limit is taken from the ultimate strength multiplied by 0.5 of the material. Now, if the material is involved in shear intorsion, we will be applying a factor, which before we have taken that a certain factor for axial loading, which is equal to zero point 0.8. Now, for material, for an element subjected to shear intorsion, we will now consider that the strength reduction factor for axial loading, not the axial loading, but the shear intorsion factor, which will now become equal to zero point 0.6. For axial loading, it is 0.8. For shear intorsion, it will be multiplied by 0.6. So that will be elaborated by the time we are going to apply it on some problems involving variable loads with stress concentrations. Now, considering variable loads with stress concentrations, we will still be considering what we call a material or an element subjected to limited life. So, if the element is subjected to a limited life, we will be considering factors. Another factor for considering the endurance limit or the endurance strength. The endurance limit in here with a subscript or with yes, that is S and prime. Meaning to say S and prime is the fatigue limit or the endurance limit. That is different from endurance strength. Endurance limit is taken equal to 0.5 multiplied by the ultimate strength of the material, which the endurance limit now, or the endurance strength, endurance strength is equal to Sn prime multiplied by the quantity 10 to the 6 all over mc raised to a power of 0.09 for limited life. Nc in here is the number of cycles. Number of cycles or the limited life. Or that can be also sometimes equal to whichever is applicable. That is Sn prime multiplied by the quantity 10 to the 6 all over nc raised to a power of 0.085, which we will still be considering Kf. The Kf, as stated, fatigue strength reduction factor, that is with a subscript, small letter L in there, meaning that that is the Kf for limited life, which is now equal to, that is n raised to a power of log Kf all over 3, all over 10 log of Kf, or n raised to a power of log Kf all over 3, all over Kf. That is for the Kfl. That is for limited life. Meaning, if we are going to have or take the equation involved for the Soderberg criterion where limited life is applied, this Kf in here, this Kf in here will be changed by the Kfl, meaning that is the fatigue strength reduction factor for limited life. So to used for the endurance strength for limited life. Before, for variable loads, endurance strength for variable loads without stress concentration, we have taken or have already taken the value of the endurance strength. While in here, that is still the one that will be considered is the endurance strength for limited life. So to find for the endurance strength for limited life, that is now the endurance strength taken with the application or the endurance strength taken in here for limited life. So that is the one that will be applied in here with the corresponding different factors that are applicable. We have the surface factor, we have the size factor. The surface factor, of course, previously taken from figure AF5, page 580, design of machine elements by Virgil Morin. That is for the surface factor. For the size factor, it was arbitrarily taken equal to 0.85. Now, this factor for axial loading, this is for axial loading. So if there is no axial loading that is involved, this will be removed. FAL will be removed. If there is a shear intorsion, pure shear intorsion, that will now be changed. This is equal to 0.8, that will be changed to 0.6 for considering the endurance strength for limited life. So that is the difference in considering simply the endurance strength and the endurance strength for limited life. Now, bear with me, viewers and listeners, bear with me to please, to be able to clear these things out. I suggest that you have to read the books by Design of Machine Elements by Virgil Morin involving variable loads with stress concentrations. There is no other book that I know that have taken, that have considered variable loads with or without the stress concentrations that is as how the Design of Machine Elements by Virgil Morin have taken. So bear with me, please read that book so that these things will still be cleared out for you. I actually have having difficulty in trying to show, to be able to visualize the meaning of all these things. Now, this can be seen and this can be applied or maybe easy to understand if we are going to apply them on different problems. So we have here a problem which involves the stress concentrations. As stated, the load on the link shown is a maximum of 10 kips, repeated and reversed. The link is forged from AISI C1020 steel scroll, and it has a drilled hole on the center line of the wide side. Let X is equal to 2B and N is equal to 1.5. Determine B and X at the hole. No column action involved. For letter A, for indefinite life. For letter B, for 50 repetitions. No reversal of the maximum load. For letter C, for indefinite life, but for a ground and polished surface. In this case, compute the maximum stress. A and C are actually the same except for the surface it is as for. For letter C, it is for a ground and polished surface. So we have here the diagram with the given maximum load of 10 kg repeated and repaired. Material as AISIC and 20 kilos and left as quartz. Center hole is 114, X is equal to 2, and is equal to 1.5. So we are asked to find for the dimensions X and B for A, B, and C. So the solution will start from the property of the material, which is taken from table 87, page 576, design of machine element for AIFI, secant 20 kilotons. Ultimate strength is 65 KSI, yield strength is 48 KSI. To find for the endurance limit, the endurance limit is equal to 0.5 of SU, or that is 0.5 of 65 KSI, which is now equal to 32.8 KSI. Then, from figure AF5, page 5 and 3, design of machine element by Beryl Morin Paynes for surface finish as forged, we will be able to have it equal to 0.55. So the size factor was arbitrarily taken at 0.85 and the axial loading factor is 0.8. So we will be able to take the endurance strength. The endurance strength now will be equal to 0.8, 0.85, 0.55 by 32.5, 32 point. $32.5. So that will be equal to 12.2 KSI. Again, to be able to find for the KF, we have to consider figure AFA, page 584, kind of elements by Virgil Morin Paynes. For a drilled hole that is B over X greater than 1, we assume KT at 3.5. From figure AF7, page 584 of the design of machine element by Virgil Morin-Page, where R is equal to P over 2. R is the radius of curvature, P small letter P is the diameter of the hole, divided by 2, that will be equal to 1 over 8 or 0.125 over 3. The value of 8 taken at 0.01. So we will consider the notch sensitivity factor equal to 1 over 1 plus A over R, or 1 all over 1 plus 0.01 over 0.125. Q now will be equal to 0.926. Having the value of Q, Kf now will be equal to Q multiplied by the quantity Kg minus 1 plus 1, or 0.926 multiplied by the quantity 3.5 minus 1 plus 1 will give us 3.3. For repeated and reverse flow, the mean stress will be equal to 0. The alternating stress will be equal to F, that is maximum, all over divided by 2, all over, or the maximum flow, all over P multiplied by F minus P. That is the cross-sectional area at the section where the stress pressure is, which is a drilled hole, that is X minus P, or that will be 10 all over P that by the quantity to be minus 0.25. So we have taken all the factors involved for considering, that is finding for B and or B and H. That is for the dimensions of the thing. Which for letter A, from the Soderberg line criterion, 1 over L is equal to Sm over Sy plus Kf multiplied by Sa over Sn. So substituting values, that is 1 over 1.5, this is equal to 0, so that is 3.3 times 10, all over P multiplied by the quantity 2B minus 0.25 multiplied by Sn, which is 12.2. So the equation will be reduced to 2b squared minus 0.25p equal to 4.06. So to have it in the quadratic form equation, that will be equal to b squared minus 0.125p minus 2.03. Applying quadratic equation or quadratic formula, we will be able to find for B equal to 1.489 inches. So we use 1 1/2 inch. Then X is equal to 2 multiplied by B, or 2 multiplied by 1.489, which will be 2.978 inches. So we will use X is equal to 3 inches. For letter B, for 50 repetitions or cycle. So, as I have stated a while ago, we will be considering the endurance strength for limited life, which is taken from the endurance limit multiplied by this term in here, which we will be able to have equal to 50.988 KSI. So for the endurance strength for limited life, the value we have taken here, that is 50.988 KSI multiplied by the size factor, multiplied by the axial loading factor, multiplied by the surface factor, 0.55. That will give us 19.089 KSI. For our strength or fatigue reduction factor for limited life, which is taken from here, that is 5 times 10 to the 4th raised to the power of log 3 over all over 3 all over 10 raised to log of 3.3. That will give us 2. Substituting all values, that is 1 over 1.5 equal to 2 times 10 all over B multiplied by the quantity to B minus 0.25 multiplied by Sn, that for limited life 19.069, or it will be reduced to a quadratic equation b squared minus 0.1258 minus 0.787 equal to 0. We're applying quadratic formula or quadratic equation. We will have b equal to 1.021 over t. Or we can use b equal to 1 and x will be equal to 2 times 1.021 inches. Will give us 2.042 inches, or we can use 2 inches. That is for limited life. For letter C, we are asked to find for the maximum strength, which is equal to Kf multiplied by the maximum force divided by the cross-sectional area at the section where the stress ratio is. So that is P multiplied by X minus T. From figure A5, for ground and valleys, that is our surface factor is taken at 0.93. So to get the endurance strength, we simply multiply the fatigue limit or the endurance limit by the surface factor, by the size factor, by the axial loading factor, which will be equal to 20.553. So we will have the equation here equal to 1 over 1.5 equal to 3.2 times 10, or that will give us the sizes. That is B equal to 1.174 over 8. We use 1 and 1/4. For X, that is 2 times 1.174. That will give us 2.348 inches. We use 2 and 1/4. For P over X greater than 1, we will have P over X equal to 0.111. From figure AFA, page 584, design of machine element by Wilhelm Morgenfeld, we assume KT at 3.5. Therefore, KF will be equal to Q multiplied by KT minus 1 plus 1. The latch sensitivity factor multiplied by the quantity theoretical stress concentration factor minus 1, or that will give us 3.315. Substituting all values on this equation, that is the maximum stress, is equal to 3.315 multiplied by 10 all over 1.25. That is the computed value for P. And 2.25, that is the computed value for H. Minus 0.25 equal to 13.26 KSI for the maximum stress.